Hello everybody for a new week, final week. So we're going to be doing today, I suppose, not very mathematical things. But the idea is that you will think about doing experiments, about designing studies. And so we're going to see how that goes. Now, a few things first. First of all, people have asked me, there's two things I've been asked that I will go through. Tomorrow I will talk a bit about this idea of continuity corrections, because it's confusing that essentially when you're doing a test or calculating an interval or calculating a p-value, you can get different answers by slightly different assumptions. And I realized that I thought, oh, I won't bother to talk about that. But I realize it is difficult and confusing when there are these multiple ways. So I'll talk about this tomorrow. The other thing, which I know is difficult, is about this one-sided and two-sided tests. So the first thing is, if you're doing a test using a normal distribution, in other words, you're testing usually whether some value is 0, then a one-sided p-value is, and you observe this is your estimate here, your one-sided p-value is the probability of getting something bigger if this is really true. And typically then you double it to give a two-sided p-value, because you're also calculating the probability of getting something equally extreme the other way, and you double it. If you're doing a chi-squared test, it is automatically two-sided. You don't have to double it. It's always looking at high values. And the reason is that a chi-squared on 1 degrees of freedom is just the square of a normal. It's a square of a standard normal distribution. And that means that high values of this correspond both to this and to that. So if this will be up here, if this is 3 or minus 3, this would be 9. Is that okay? So if you're doing a normal, you have to maybe double the p-value, but a chi-squared, just look at the top values, the high values. Okay, it's confusing, isn't it? Okay, I'm not sure what else I can say about that. If people still find that really tricky, ask me and I can go over it again. Can we give out the little quizzes, the puzzles? Yeah. Can we give those out to people? Right. We're going to give you a very short little question, a few small questions. Don't only look at your sheet of paper. Don't look at other people's. Just look at it's folded over. So unfold it and just go like that, like you're in school. Do your question. So just hand them out to everybody. Yeah. So you can look at them and start filling them in. Only simple questions. Again, it's anonymous. We're not marking you on this. Just don't show anybody else. Don't look at other people's paper. It's very important you do not look at other people's. Just look at your own piece of paper. Don't expect you to know the answer to the second question, just to make a judgment. Don't expect you to know. So when you've finished, can you fold the piece of paper over again and just hand it to the middle, and someone will pick them up. And then, do you think the tutors, in the blink of an eye, could if you pass them to the end of the row when you've finished, could calculate the averages within each group. So when you finish, just pass them up. No, just collect them all up and no, all together, all mixed up together. So just make sure you put a number down for question 2, the percentage of countries in the UN from Europe. So it's just a guess. You just have to guess, that's all. Okay, if you could pass them up when you've done your guess. Okay, so you're not being marked on this, so don't worry. What I'm really testing is whether the first number influences your opinion. This is actually a psychology experiment. This is psychology, not maths. I think this is psychology. Okay, have you finished? Has everybody handed in? Okay, shall I? All right, have you, everybody done? Okay, now with the trick, this is a trick. This is an exercise in psychology. We didn't pick numbers at random between 0 and 100. So everybody either got 10 or they got 60. But at random. So you have been randomly chosen. Half of you got 10 and half of you got 60. Now the hypothesis, the idea is that this number, which is completely irrelevant, might influence your opinion about, in question 2, the number of the UN from Europe. And the theory is that people who were given a big number at the beginning will actually assess a bigger number for that. Now, there's no reason, this is just psychology. This number has nothing to do with Europe or the UN. So, we're just going to test whether you've done this. So, if we say, if we assume that your numbers in this group, so you've got group A here and B here, and you could say that sort of theta A equals the average guess in group A, and theta B is the average guess in group B. So H naught, what's H naught? The null hypothesis. The thing we might be trying to disprove. What would H naught be? Sorry? There's no difference. Yeah, H naught would be that theta A equals theta B. There's no difference between the groups. Why should there be? These are just random, whoever got sent. But H1 is that, theta B should be bigger than theta A. Maybe we should just say not equals to. You do a two-sided. That would be a one-sided test. Maybe this group will have a smaller guess than that, which would be strange. So we're going to test that hypothesis. But the main thing is we've done an experiment, a random experiment on this. We'll test it. Okay. And we'll see if they can come up with the answer, or at least an estimate. We might get the estimates. To actually do the test, we need to know the distribution. Okay. On the other side of it, I'm very lucky to be here, or you are very lucky to have me here. Yeah. On Friday, I was nearly killed. Look at this. Yeah, Professor Risk. So this is on Friday. On Friday, after the lesson, I went to have lunch at Colk Bay, and a big wave came in and hit the windows and smashed the windows in, like that. Yeah, and I was just having dinner just there. And only one person was hurt. One person was taken to hospital. So I was very lucky. So it's just to show that these surprises can happen. There's a warning to you all. I don't know what the probability of that happening was. Actually, it is. It's very mathematical because it was a freak wave. I think, 2 waves came in and joined together or something, and a freak wave smashed all the windows in. So there you are. It's a lesson for us all. Okay, what I'm going to be talking about today, we're sort of doing things in the wrong order. We've done about visualization, and we've done modeling data as random variables, and we've done inference, estimation, confidence intervals, p-values. And now we're going back. Maybe we should have done this first, to how we collect the data in the first place. Now, in a way, this is part of statistics. It's not really part of the mathematics of statistics, although it is related. It's more the process of doing statistics. So when we finish this, you're going to go up and carry on with the practical work doing real statistics. But this is to do with the story, with actually how we collect the data. So what I'd like to talk about are doing surveys, doing experiments, and observational studies. And there's a good website here, a tutorial. Actually, it's rather good. I didn't see these before. StatTrek. It's a rather good tutorial on all aspects of statistics. So again, if you want something to read which explains things perhaps in a slightly different way, this is a nice website. Okay. Now, we start with something quite technical. The crucial thing, what we want to avoid, is bias. These 2 terms are used. We use bias and error. And bias is something really bad. Error is not so bad, or at least we can deal with it. So, to use our notation before, if we take a big enough sample, we know that the estimate, asymptotically, should go to the true value. All our theory depends on it. Our maximum likelihood estimation, our confidence intervals, depends on if we study enough observations, we will in the end get the true value. But bias is when even with a big sample we get the wrong answer because we've done a bad study. And technically, it's when the expectation of our estimator minus the value we want to estimate, the true value, does not equal 0. It's a biased study. Because, as we'll see, we've just done we've asked the wrong people, or we've measured the thing wrongly, we got a bad study. Now, sampling error does not mean a mistake. Although we use the word error, it does not mean a mistake. It's just another word for the standard error, which we've called square root of v, which is also can be written for a sample mean to be sigma over root n. Sigma is the sample standard deviation. Because we know that will just get small as we get more people, bigger. The confidence interval will get tighter and tighter and tighter, but we want to make sure that we get the right answer. Okay. So, let's say we wanted to do a survey. Okay, here's a question. The university you went to, how many what proportion do you think of the students in your university were on Facebook? What do you think? It's not 100%, is it? Well, what roughly do you think? Do people, a lot? Most or not? How many, somebody say a number. 10%. Oh, right. Anybody, 10%, not that, so many. Anybody with more? About 70 to 80%, you think? Do you know? Or do you know or not? Okay, you think. So big variation, maybe, of different universities. Yeah, okay. So that's a reasonable question. So what I'm going to ask, so let's say we wanted to find out. We wanted to know how many of the students are on Facebook. How do we try to do it? Well, if we can get, first of all, how many should we ask? If we want to do a survey, if we want to get an accurate estimate. And there's some nice simple maths to tell you almost the maximum number you need to ask. If you ask a random sample of students, you could really pick students at random, and if you ask 1,000 students, you'll get a proportion on Facebook. So you get 1,000 students, you say, are you on Facebook? 300 say yes, and so your estimate is 30%. And if it's a good sample, then that's an unbiased estimate. On average, you will get the right answer. Yeah, we think it is around 30%. Now, remember the formula for a binomial variance is p times 1 minus p divided by n. That's for when you divided the binomial count by the number of observations. So here we've got the estimated proportion. Now, this is something I know that people have found confusing, so worth revising always is that if I have a binomial, x is binom np, then the variance of x is what? Yeah, np times 1 minus p. But if I have x over n, so this is the actual observed proportion, what is the variance? What is the variance of x over n is p times 1 minus p divided by n. So we've got to remember, if we're talking about the actual number of cases, it's got this variance, because it's a big number, big whole number. If we're talking about a proportion, it's p times 1 minus p over n. Dividing by n, you have to divide by n twice, because you divide it by n squared. Okay, so that tells us our standard deviation is p times 1 minus p over 100. Now, the neat trick is to realize that this is a maximum when p is a half. If we draw that standard deviation, if we draw this, it goes like that. Whoops. If this is p times 1 minus p over n, and this is p, the variance is biggest at a half. When p is very small, this gets very small, goes to 0. When p is near 1, it goes to 0. So the biggest variability is around 50-50. So we know that the maximum of this, when we put in p equals a half, is that practice? Is there a fire person? Yeah. Don't panic. No, we're all right. Right. Calm down, everybody. Don't worry, I would be first out of that door. No. I would say after you. Yeah, no, I'm the oldest in the room. I'm allowed to be first, I think. Actually, no, I should be last if I'm the oldest, I think. Yeah, exactly. I should be last if I'm... Okay, I'll be last. If there's a fire, I'm last out. Okay. Let's agree on that. Okay. All right. Okay. Yeah, when you put in p equals a half, you get a half times a half. So that, I think, check my maths, I think should be 1 over 4,000. And that, when I put in my calculator, is 0.016. Okay, so the standard error is at most, if you have 1,000 people, about 0.016, just slightly under 2%, about 1.5%. So a 95% interval, which is plus or minus 1.96, about 2 standard errors, is at most, the widest it is p hat plus or minus 0.032. 3%. That means, it's a wonderful result, it's really neat, that if you ask 1,000 people, you should always get the result within 3%, or nearly always get the result within 3%. However big the proportion is that you're estimating. So whether it's 10% or 70%, if you ask 1,000 people, as long as it's a random sample, not biased, then you should get within 3%. So that's why, certainly in the UK, in Britain, when they do surveys, they're always of 1,000 people. All the surveys in the newspapers, 1,000 people. That's all they ever ask. They just ask 1,000 people. It doesn't matter how big the population is. There could be 50 million people in Britain, there's 60 million people, but if they want to know how people are going to vote, or whether people believe in global warming, or whether they do whatever they do, they always ask 1,000 people. Yeah. No, it depends what you're interested in, because you might be interested in subgroups, smaller groups, and this will not work for if there's smaller groups you're interested in. So this is only if you're answering a single question over everybody, and 3% is good enough. If 3% is good enough, because 3% might not be good enough. Maybe you want to know within 1%. You'll need a lot more to do that. Yeah. But it just shows really what you're saying, that you can plan ahead and plan how many you might want. Okay, so that's the idea. Okay, so let me just... I want to actually make you think about this a bit. If you were in your previous university and you wanted to know the 10% or the 70%, how do you think you would do it? How would you ask the students? How would you wanted to do a survey, how would you say of 1,000 students or 100 students, how would you identify them? So could you actually stop, talk to, discuss. So give you 3 minutes to talk to each other. So maybe just in pairs or in threes. If you start talking, to just don't all turn left, because then you're speaking to the back of someone's head. Yes. If you all turn to the person on your left, no, that's no good. Every other one of you should turn right. Okay, so what I want are some plans for doing the survey. How would you ask people? Okay? Right, ideas. How would you do it? You would divide them separately for males and females. How would you find out? Okay. And then how are you going to sample within males and females? Yeah, okay, but you're not going to go and ask every male in the university, are you? Yeah, no. What you're saying there is called a stratified sample, that you would check within each group, perhaps estimate them separately. Okay, so you could do it by year. Do you think there would be a difference? There would be a difference by males and females on Facebook? No? Equally likely, do you think? Okay. How would anyone any ideas about sampling? How would you get hold of people? How do you find them? Do you just stop them when they're walking along, when they're coming out of a lecture or something? How would you identify 1,000 students? Now, how do you pick people at random? The registration, very nice. So what would you do? You would find the registration numbers. And so, but has every student got a number? Every student will have a number. Okay, so then let's say you've got those in a list. If you did, so how would you then pick them at random? Put them in a in a big hat. You get Emil's hat and put them all in. Pull them. Yeah. Now, how would you? If that was a computer file, how would you choose 1,000 at random? Okay, so we've got and in R there's, I can't remember what it's called, but there's a function to randomly choose. Yeah, okay, now this is very good if you can get hold of the computer file. Now, but then you've got the numbers. What do you do then? You've got to find these people. How do you get hold of these people? Go on, then you've got the number. Let's say you've got these numbers. You've got 1,000 random numbers. How do you find out if they're on Facebook? You could send emails. Are they all on email? Are they all on email? Do all students use email? Oh, right. So, yes. So you use Facebook. Now that's the other way to do it. So use Facebook and try to find everybody from the university. Now, in fact, this is quite interesting. How you said you could run a competition. Are there other ways you could do it by using Facebook? Because this is actually quite an important thing with new way people use thing on social media. I mean, could you use people's friends? Because one possibility is to, you could start with your friends and then ask them to contact their friends in the university, and friends, and you try to find out. Well, okay, so this is it's a different way of doing it because it's actually trying to find everybody. Yeah. Okay. Do you think it would work? Yes. You search for them on Facebook. Oh, I never. Yeah. What about people who don't? That's really nice. Would it work? Would people usually use their? You say would it not work? You wouldn't find them. Sorry. Completely different. And you can't on Facebook. People would usually mention the university. Can you search for that? You can search for everybody with that. Yeah. Okay. So that might work. Yeah. Okay. Oh, that's very good. Yeah. Okay. That's. What's happened here? Yeah. Okay. No, there's some good ideas. And in fact, what you defined is these different ways. There are different ways to do this kind of thing, which I've just written some up here. And one of some of these are good and some of them are bad. There's the asking for volunteers. That's a bit like searching Facebook. That's trying to find everybody. It's not like doing a sample. You actually are trying to find all the people. Yeah. The other one, which nobody said, I think people knew it was a bit daft, is the convenience sample, which is just when you ask, your friends or the people you meet in the street or something like that. Now, in a university, why would that not be good? If you stood outside a lecture and asked people, would that be good? What would be wrong with that? Sorry? Would it?
Because if at university we have many departments or faculties.
Yeah. And do you think it would differ between faculties?
Yes.
More people in computer science and in history? Yeah, exactly. Because if you stood outside a computer science lecture and asked people, it would be hopeless. You'd get 90% or something. So, this shows it's the real danger that you can get the wrong answer. So, the best way is, the simplest way is this simple random sampling. And that's this one. This is you get a file of everybody, pick them 1,000 at random, find them, and that seems to be, probably the best, most efficient way. And the stratified sampling, again that was suggested, is when you might go to different faculties and ask separately within each faculty. Because then you get more information and you feel more robust. And then there's this method called cluster sampling, and that would be like if you just picked, I don't know, maybe if there were some student houses or something like, you just picked a couple of houses and asked everybody there. Now, we're going to see some of these on, so for example, the South African Victims of Crime Survey, VOCS, has just come out, and that uses a form of cluster sampling, where they sample areas of South Africa at random, go in, and then systematically work through all the houses in that area, asking them whether they've been a subject of crime or not, a victim of crime. And you can see that's more convenient. If you're doing door-to-door interviewing, it's much more convenient to do a whole lot together than one that's dotted all over the country. So these are used in different ways. And the point is that we're not going to do that, but there are all technical techniques for adjusting the confidence intervals for these different methods. We've just learned about this one, simple random sampling, but there are all sorts of other techniques, which we won't go into. But yeah. Okay, the crucial thing is the sampling frame, like this, that's called the sampling frame, should be a representative sample. And so things go wrong if there's some people who are never asked, maybe if some people were not on the registration form, or when people are asked and don't answer. Because that's one of the problems. With this, in a way, the Facebook is quite nice because you can find out without asking them. But if you just ask somebody and they said, I'm not telling you, or just sort of ignored you, said, excuse me, are you on Facebook? And they just went, huh, like that, and just walked away. You're left, well, what do we do? Do we put them down as a no or a yes, or I don't know. And of course, these things can happen, especially with perhaps slightly embarrassing questions. People may not want to answer them. And you can't just then take the data you've got. So there's a lot of problems with these. So in the US, they always use telephone surveys. So they pick phone numbers at random, phone people up, and ask them what they think about gun law or global warming or something like that. Would that work here? No, I don't think it would. No, I mean, people have got mobile phones. I suppose you could pick mobile phone numbers at random. I don't know. Usually this is always with home phones, but people don't have home phones anymore. Internet surveys. What's the problem with internet? Going on with the internet, asking people, surveying people on the internet about what they believe in, or are they on Facebook or something like that? Exactly. There's a very biased sample of internet. You only get the internet users. So you're missing out huge amounts of the population. And this is the one. Do you listen to this on radio shows? People say, oh, phone in and tell us what you think about something or other. Yeah, those are about the worst ones. That's the worst one. Because nobody's going to phone in unless they've got a strong opinion about something. Yeah. But it's remarkable how often in newspapers you get these voluntary surveys and they are of no value at all. Okay, so things can also go wrong if you ask the wrong question. So this is a joke. I don't think this question has ever been asked in a survey, but this is a standard. Have you stopped beating your wife? So if you answer no, people will think you're still beating your wife. And if you answer yes, it sounds like you were beating your wife, but now you've stopped. So that is the standard example of a leading question, a really bad. But that's obviously stupid. But people can ask questions like this: do you think the police are doing enough about the terrible crime problem? What do you think people are going to answer for that? Yeah, they're going to say no. They're not going to say, oh, yes. It's a really leading question. And yet you see these quite a lot. So if somebody publishes a survey, you should always see what is the actual question being asked. So look out for those things. So, okay. Now, experiments. Shall I tell you the result of our experiment? Do you want to know? Is it cool? Well, I've rubbed them off now. Okay, we've done an experiment. Okay. So, X bar A and X bar B, this is the mean of people who had X equals 10 at the top of their piece of paper. And the average for that was, Emma? 30.25%. So people who were given that number at the top, a meaningless number, thought there were 32.5 states in the UN were from Europe. The people who are given X equals 60, the meaningless number, now do we think it's going to be about the same? Bigger? Smaller? How much bigger? More. And the answer is Emma? Oh, no, Brenda? 46%. Nearly is more than 50% more. So that was the average of the people in the audience who were given that, and the average given that. Isn't that amazing? It's amazing. Now, we haven't tested if these are significantly different or not. So the means are different, but the P equals, what's the confidence interval for the difference? We don't know. I think it is. I guess P equals less than 0.05, but I don't know. Because what we've got, and we'll look at the data, I guess you'll probably get this tomorrow to look at. You've got two groups of data. You've got the A's, so these are the A's, and you've got the B's, which are slightly bigger. This is about 30, and the B's will look like this, be a bit bigger. But I don't know how spread out they'll be. They could, if they're really spread out, these differences might not be significant. So you don't know yet until we see how spread out they are, because the p-value depends on the variance of them. Okay, so it worked, I think. There's 170 nations in the UN, I think. I would guess there's about... No, I think it's a bit less than that, in fact. Yeah. Actually, to be honest, this question is given usually in Europe, and they ask the percentage of nations in the UN in Africa. The usual question is to use Africa. But I thought, well, you might know that. so I wanted to use something that you might not know. That was the trick. So anyway, it seems to have worked. What this shows is, this is both an experiment, and it shows the wording is incredibly important. What you're told at the beginning of an interview can change what you think. And I'll do another little one tomorrow, another little psychological test tomorrow. Let's move on. You'll get the data for this tomorrow. Let's move on to experiments, when we actually want to see about an intervention works. Now, okay, I'm going to set an example here, another thing for you to discuss. Suppose we wanted to see whether what are called conditional cash transfers reduce the spread of sexually transmitted infections, STIs, in a rural African community. Now, have people heard about these conditional cash transfers? Have you heard of them? No, I hadn't either. I just was researching this. It's amazing. It's when somebody or a couple are given money to come and be tested for sexually transmitted diseases. They only get paid if they're negative. So you lose your money if you develop an STI, if you develop a sexually transmitted disease, whether it's chlamydia or gonorrhea or HIV or anything. You get paid for being tested negatively. So they're cash transfers, but they're conditional on being negative, with the idea this is an incentive towards safe sex and to reduce infection. Okay, so this is an idea. I think the World Bank and other people have been, saying this might be a good idea. Would it work? Would it work or not? We don't know. What I'd like to know is, if you were working in an organization and you were told, oh, you're a statistician, you know about experiments, how would you design an experiment to test that? So I'd just like to give you 3 minutes, turn and talk to each other for 3 minutes, have a think. It's a difficult problem. How would you test whether that worked? And you had some money, you had some funding, so someone gave you a grant, and you had a community out there, a rural community. How would you test whether that worked? So, okay, I'll give you a few minutes to think and talk to each other about that. The World Bank has given you all this money. How are you going to do this study? Any ideas? Somebody else. Go on, you've got some ideas. How would you might do it? Anybody volunteer? Yes, okay. You'd pay them just for coming? That's not what's being tested. They're not. The intervention is not just paying people to be tested. It's you only get the money if it's negative. Now, I think that's what the World Bank has told you. That's what you have got to evaluate. They only get the money if they're negative. Okay, so how might you do it? How might in a community, in a village, increase? So what you might call it, what you would look at them before and after. Yeah. Okay. Now that's a standard a technique of before and after. So you take a community and you measure, you test them, I think. Then you offer them this, and then you check after. Okay. It's done a lot. These are good, standard design. Are there any problems with that, though? I mean, let's say before, there were 2% had infections or something like that, and afterwards, after a year, 6% had infections. Would you know whether it had worked or not? Yeah, you've got to get the baseline. Yes, no, exactly. The before, they have to volunteer. Well, you could say that you can only join this study if you get tested beforehand. You're supposed to encourage them for safe sex, using condoms, not keeping to one partner. The idea is that they should make their sexual practices safer, and so it should reduce the spread of infection. For example, staying loyal to one partner or using condoms. So that's the idea. That's the incentive to do that. Yeah, they do. They get to know the result because they only get paid if it's negative. Yeah. So you should be doing time they do them every 4 months apparently. So they do 0, 4 months, 8 months, etc. That's a very nice idea. Yes, you get something for coming. You get more if it's negative. Yeah, no, I think that's a good idea. But in fact, that's not what. What was that? Can anyone see a problem with just looking at what happens, monitoring, even over a long period? What's the problem with this? Even if let's say we knew this was 8% or 10%, what's the problem? You don't know. In a way, yes, exactly. There may be other factors coming in. How can you get rid of these other factors? Is there any way, do you think? How can you control for these other factors? Okay. Shall I tell you? Shall I show you? I will show you the answer. So that's all right. Have you any other ideas on this, on how you might do it? And that's the crucial point, is that, well, we don't know what would have happened if they hadn't been paid, these people. Maybe this would have happened, maybe it would have been worse, maybe it would have been better. We can't know. And so these are some broad, options. Because one of the things, you could just compare one village with another, people who got it and didn't. This is the before and after. You observe what's happening and then introduce cash transfers. But this is the crucial one. You randomly allocate people to be offered the cash or not. Some people get it, some people don't. And you compare those two groups. So that's the basic idea for how you control for these other factors. You have two groups, and the only difference between them is that one is being offered these cash transfers and the other isn't. And that should control bias. The resulting differences between the groups must be either due to chance or the intervention. So that's the basic idea. And remarkably, it's been done. Just been published. Earlier this year, it's just been published by, in the BMJ Open. The paper is on the website. It's freely downloadable. Incentivizing safe sex, a randomized trial of conditional cash transfers for HIV and STIs in rural Tanzania, and with a big list like that. So they've done, and I think it was the World Bank funding this. So they've done it, and I wanted to show you. I thought this was remarkable, brave thing. Now, it's in slightly small writing, but I'd like to go through this. Look, they evaluated the use of conditional cash transfers. It's an unblinded, individually randomized and controlled trial. And I'll talk about the unblindedness. They chose 10 villages in an area in rural southwest Tanzania, and involved 2,400 people were enrolled. So they've got 2,400 people, and this is the amazing bit really. They got them to agree to be randomly allocated. So you had 2,399, and at random then 1124 of those were chosen for the interventions, and the remainder didn't get anything at all. Nothing. So half of them got the intervention, half of them were just normal. And of these ones that got the intervention, these were randomly allocated to two groups. The ones who got $10, which I think is about 10,000 Tanzanian shillings each test, and the higher group, which got $20. So some people got more than others, to try to give an idea about whether it was only effective if you actually paid quite a lot. And this was all done at random. I'll show you how it was done. It was interesting how it was done. And they tested participants every 4 months over a 12-month period for common sexually transmitted infections. Anyone testing positive for a sexually transmitted infection didn't get the money, but they were offered free treatment and all received counselling. So that was one of the incentives. You get free medical treatment if you join the study. Okay, so main outcome measures here. So they test every 4 months. They tested for chlamydia, gonorrhea, trichomonas, and mycoplasma. And at the end of the year, they tested for HIV, herpes simplex virus, and syphilis. And then they do all this at the end of the 12-month period. Now, I'll talk tomorrow about the details of how you get these numbers. They produce an unadjusted relative risk of 0.8 for the high value conditional cash transfer arms to compare with the controls. So that means that if the control infection rate and this is the high, this is the $20 rate, was 0.8. So this group had 20% fewer infections than the control group. So this group, $20, had 20% fewer infections than that group. So paying people $20 every 4 months reduced apparently the infection rate by 20%. One in 5 prevented over a year. But notice they got a confidence interval. 0.54 to 1.06, it doesn't, it includes 1. P is not less than 0.05. The confidence interval includes 1. But they managed to, by doing some statistical adjustment, they bring the confidence interval to just not include 1. Remember, that's the magic thing. Get your confidence interval, which shows there is a significant effect. We'll talk about the adjustment later on, etc., etc. So what they suggest is that the $20 seems to work. That's what they suggest. The $20 works and the $10 doesn't. No. They found a reduction for the $20 payment, but no such reduction was found for the group receiving $10 payments. And they say we should do more studies. So they actually did this study and found what looked like, even though it wasn't really, even with 2,000 people, it still wasn't really big enough. So an effective strategy. So we can look at more of that data. Any questions on that? I'll send out the paper. Yeah, any questions? The interesting thing of this, there was the randomization. How did they allocate them at random? They actually did it in the middle of the village with a bag of balls. They had a bag of selecting coloured balls from a bag to decide whether you were going to be in which whether the control treatment or be offered the cash. So it was done publicly, and they say this was for acceptability of randomization. They did it all publicly, and so that everyone could see what was going on. Yeah. So that's just an example of an experiment, and that's what people do now, using statistics. So we'll come on to we'll do some stats of that tomorrow. Okay. We've done that. Oh yeah, okay. Oh, this is a bit boring. This is good principles of randomized trials. I'll leave you to read that. This is just about how to do a randomized trial. The interesting thing is this thing of blindness. I won't go. Blindness is when you don't know what treatment you're getting. Now, the people in this trial knew what treatment they were getting, but sometimes if you do a drug, if you're testing a new drug, a new pill, people don't know what treatment they're getting. And so they produce placebos, little pretend treatments, pills of the same, that look the same, taste the same, but don't actually have anything in them. Sugar pills. And they give sugar instead. And that's done because people often get better just because they've taken a tablet, especially red ones. Apparently, if you take a red tablet, it makes you better than taking a blue tablet. You feel better. Amazing. Yeah. And if it's from a box with a nice label on it, that makes you feel even better. It's extraordinary. It rarely reproduces. This is shown everywhere in all countries. Okay. Just to sort of finish off with a bit of a joke. Randomized trials have a new pharmaceutical product approved for sale. The drug should be proved to be safe and effective. And that usually involves 2 randomized trials, each with p less than 0.05. So to get drugs approved for sale, and that's to avoid ineffective and possibly dangerous treatments. Because in the past, all sorts of medicines were licensed without proper statistical analysis. And I found some of these on the web, which I think were just wonderful. Look, this is cocaine toothache drops. So this is from America, from 100 years ago. You could buy cocaine, 1885, so quite a long time. Because people thought cocaine was really good for you. So they sold cocaine Coca-Cola used to have cocaine in it, but they took it out. So this is the kind of stuff they used to sell for children. So give your children cocaine. And this is a nice one. Soothing syrup. This is for children teething. This had morphine in it. And they used to sell this for kids and had dangerous stuff in it. The mother's friend. Isn't that lovely? Yeah. This is my favourite. Get fat. Fatten you. Corpular foods. So this was the food. It was get fat food. For that lady who obviously wants to get fat, because she's got a very slim waist, so she obviously wants to get. So this is the kind of stuff they used to sell, get fat food. And then this one is anti-fat. So this one will lose 2 to 5 pounds per week. Now, I think you can go into most magazines and see, adverts for things like this. And so the idea really is if something's going to be sold, it should be tested. It should be tested properly. Okay. I think will I do that now? Or shall we have a break? I think we need a break. Yeah. Let's have a break. Okay. Okay. Any questions on that? Because otherwise, yeah. All right. Good. Splendid. Let's carry on with because there was a lot of work in the practical last week. So I think I'd like to carry on with that upstairs to get on with the R, and so we can answer any of your questions on it. And the thing I didn't test, because I did say on one of them, can you find a program that will draw nice little confidence intervals like this to compare? And I haven't checked that yet. Does anyone find one? Anyone's found one? There must be one somewhere. I'll have a look in. I'll just Google it. Yeah. Okay. Right. It's all right. Let's stop.